So we're looking at example 6, and in this example you have a 1 liter solution, and you have 2 separate acids in it. You have 0.1 mole of acetic acid and 0.05 moles of hydrochloric acid. So when you're looking at this, again, let's figure out a type and strategy before we just dive into it. We can plan this out. First off, as far as the type, we have 2 acids. We have a weak acid, WA, weak acid, plus we have a strong acid. And these two are going to affect each other. Now, the strong acid is going to dissociate 100%. This one, the acetic acid is not going to dissociate 100%. And the fact that we have other sources of hydrogens is going to affect the concentration of the acetic acid. So the strategy here, we're going to want to use icebox, and the strong acid is going to present a common ion. So those are some things to think about as we get into this example. Eventually, we're going to find the concentration of all species. We're going to find the pH, the pOH, and the percent ionization. So the first thing we're going to do is start with the dissociation reaction of our weak acid. Acetic acid, and it's going to yield hydrogen ions and acetate anions. And this is going to be the basis for our icebox. Now, the weak acid is the basis for the icebox because only a certain percentage of the acetic acid will dissolve. We do not want to start with the strong acid because it's 100% dissociation. So it won't be helpful to start with that one. So we're going to list everything that we know here. In the beginning, we know that we have 0.1 moles or 0.1 molar of the acetic acid. We also know that we have some existing HCl, which means this is all H+. So we have 0.050 moles of the H+ ions. And at the very beginning, there was no existing acetate, so we're going to mark it as a 0. Quick note, everything has coefficients of 1. They're in 1-to-1 ratios. That makes this one a little more straightforward. So when we dissolve this acetic acid in water, it's going to change by X. The concentration of this will decrease by X, which means the hydrogen increases by X and the acetate increases by X. And so at equilibrium, acetic acid is 0.1 minus X, hydrogen ions 0.05 plus X, and acetate is X. Now, eventually, what we're going to be interested in is the hydrogen ion concentration. So it's going to be the information that comes out of this box. But in order to find that, we have to figure out X, which means we need to use the equilibrium expression. So K, and this is a weak acid, so it's Ka, K for acid. On top, we have concentration of hydrogen ions, concentration of acetate ions, and again, everything is in 1-to-1 ratios in the equation, so the exponents are all 1. So we have some values. This is our H+, this is our acetate. So we can plug these in. On bottom we have the acetic acid. Try that again. And this question doesn't give us the value of K, but if this were the AP exam, it would. Probably not directly in the question. Usually, the value for K would be somewhere up the page, and you would have to hunt it down. It won't take long. You just have to know that we need to look up the page. And so this is a situation where we look back to example 3 of the same section, and it tells us the Ka. The Ka equals 1.8 times 10 to the minus 5th for acetic acid. This is a pretty small number, which means not very much of this acetic acid is going to be dissolved. Compared to this 0.1 mole, it's going to be extremely small, almost 0. It's much, much less than 0.1, which means we can take this nice shortcut of making this minus x disappear. It's going to make our math easier without really changing our numbers. And so we'll go ahead and solve. And I'm going to skip some steps here, but you're going to solve for x, and it's going to come out to 3.6 times 10 to the minus 5th. And then we can sub this back into our equilibrium. So first off, the acetic acid concentration. It's 0.1 minus x, which is 3.6 times 10 to the minus 5. And it comes out to be, with rounding, 0.100 molar again. The concentration of hydrogen ions, 0.5 plus x, and it ends up not changing very much, 0.050. Again, if you went to maybe 6 or 7 significant figures, you would see the difference, but using 2 or 3 significant figures, it's rounding off. We're not even seeing the difference. Concentration of the acetate ion is x, 3.6 times 10 to the minus 5th molar. Let's put our units in. So these are the species. I suppose if you wanted to include chloride, you could. It would be 0.050, just like the original hydrogen was. But we're more concerned about species in the weak acid dissociation reaction. So pH is the negative log of the hydrogen ion concentration. And before we do this, let's just pause and estimate So this is really 5 times 10 to the negative 2. So we're looking at something between 1 and 2. Just as a guess, it's probably going to be 1.5 ish. Let's put it in our calculators, and so we find that it is 1.30. Close estimate, not exactly 1.5. They'll do that to you on the multiple choice section, though. They'll say, what's the approximate pH here? Is it 1 to 2, 2 to 3, 3 to 4, something like that. Just know that you want to be able to estimate it. And to do that, change this to scientific notation. And it's going to be approximately the value of the exponent. It also wants the pOH, and the short way to do this, 14 minus the pH, and that is 12.70. And the hydroxide concentration, which it didn't really ask for, but we can figure it out. 2 ways you could have found this. You could have used the Kw equals concentration of hydrogen times concentration of hydroxide. That would be fine. Or now that we know the pOH, probably just as easy. It's 10 to the negative pOH, which this is not an appropriate answer. You have to actually put it in a calculator. Once you do that, it turns out to be 2 times 10 to the negative 13. And it has units, it's molar. And see, the exponent negative 13 is very close to 12.7. And so you can maybe see the association between the numbers. The next question it's asking is the percent dissociation, which we usually get towards the end of these questions, and there's not a whole lot of discussion on it. But this is the value of X minus the initial concentrations. And of course it's a percent, so you multiply it by 100. So it is 3.6 times 10 to the negative fifth, and the initial was 0.1 molar, and we end up with 0.036% dissociation. This tells us that less than 1% of this acetic acid is dissolving in this scenario. It's less than 1%. It is less than, very small. And if you compare this to a previous example, let's see here, it is example 3. If you look at example 3, we have the same concentration of the acetic acid, but we don't have any of the hydrogen or anything else, just the acetic acid. It dissolved 1.3%, and so this is much less than in pure water. And really, if you think about this reaction, you've got the acetic acid, and you've got this hydrogen ion, and of course the acetate. And as you increase the hydrogen, if you think about this like a seesaw or a teeter-totter, whatever you want to call it, so you've got this thing. If you lift this end, it's going to tip this end up and this end down, and things are going to roll this way, and that is favoring the reactants. Looking at it visually helps me, maybe does with you, maybe not. But that makes the acetic acid reaction favor the reactant, acetic acid, rather than the products, hydrogen and acetate. We'll look at one more. This is example 7, and we're working with a lot of the same numbers. We've got 1 liter, we've got 0.1 mole of the acetic acid, and this time we are adding 0.05 moles of sodium acetate. So first off, the type, we have acetic acid, which is a weak acid, and we have its corresponding salt, which the acetate ion is its conjugate base. Anytime you have an acid and its salt, it's going to affect the pH. So strategy here, same as last time. We're going to use the ice box. And we can get through this one pretty quickly because a lot of the things are the same. The dissociation reaction of acetic acid, the initials, 0.1 mole of the acetic acid, no other sources of hydrogen this time, so 0, and we have some acetate. Sodium acetate is going to dissolve 100%. Whenever you see an acid with its salt, you can assume that the salt is going to dissolve 100%. .050 moles. Same thing, as the acid dissolves, it is going down by a certain concentration. Hydrogen is going up, acetate is going up. Same equilibrium expression, Ka equals the concentration of hydrogen to the first power, concentration of acetate to the first power, over concentration of acetic acid, also to the first power. The Ka value here is the same. We're still talking about acetic acid. Hydrogen concentration is X, acetate is 0.05 plus X, the acetic acid 0.1 minus X. Remembering that X is going to be an extremely small number, we can just ignore this on the bottom, saving us some steps. Solve for X, and it's actually going to be same X that we found in example 6 because numbers are the same. We've just flip-flopped these. It is 3.6 times 10 to the minus 5th. So concentration of acetic acid, 0.1 minus X, which is extremely small, it's going to round to 0.1. Hydrogen concentration is equal to X, 3.6 times 10 to the minus 5th molar. concentration of acetate ions, 0.05 plus X, and it's going to round 0.05 molar. The pH is the negative log of the hydrogen concentration, which is 3.6 times 10 to the minus fifth. Now, before we do this, let's try to get an estimate of pH. So looking at its exponent, -5, so the pH is approximately 5. It's going to be between 4 and 5. And so put it in the calculator, it comes out to 4.44. POH, 14 minus the pH, and that comes out to 9.56. Concentration of hydroxide, 10 to the negative 9.56, which has to go in the calculator. (2.8 times 10 to the minus 10 molar. And minus 10 corresponds pretty well with the POH of 9.56. So it's looking like it's in pretty good shape. Percent dissociation, X over the initial. Same numbers as last time, and same percent dissociation as last time, 0.036%. There is a second method that you can use when looking for the pH of a solution made by combining a weak acid with its salt. And this is what's known as a buffer solution, something that we're going to get into more. So a weak acid plus its specific salt, which is its conjugate base. So it's usually this type of a combination. You have acetic acid with sodium acetate or something like that. It's usually going to be paired up, the second substance, sodium, with the anion. So method number 2 is something that we'll very briefly introduce right now, and then we'll move on. Then we'll come back to this another time. Oh, it's not working very well. Henderson-Hasselbalch equation for buffer solutions. This is on your AP formula sheet. And so looking at this equilibrium expression, this is a generic one. Here's your hydrogen concentration, here is your anion concentration, and here is your weak acid concentration. Another way that you could write this is hydrogen concentration, and then it's times the fraction of the anion concentration over the weak acid concentration. I'm not going to spend time deriving the formula for you. It is on the AP sheet. If you would like to see it derived, come see me another time. But here is the formula. pH equals the pKa plus the log of the anion concentration over the weak acid concentration. And that's the only reason this was broken up here, because you can put it in right there. If you know these concentrations like we did here towards the end, then you can do that as well. And you're just going to fill in some numbers. So when you want to know the pH of a buffer solution, this is the negative log of the Ka value, which for the acetic acid was it was 1.8 times 10 to the negative fifth. So the negative log of the Ka, which is this, plus the log of the anion concentration, which we found to be 0.050 over the weak acid concentration, which we found to be 0.1. And putting all of this into the calculator, you would end up with the same number. And once you know how to use the formula, it's less work. It's going to take some practice. Until then, we will continue with ice boxes and the equilibrium expressions.